You ever see a rocket launch? I mean, really watch it and just wonder at that raw, incredible power. How in the world does something that big, that heavy, just leave? How does it break free from the one force that keeps all of us glued to the planet? Well, today, we're going to dig into the amazing physics that makes it all possible, how rockets actually conquer gravity. I mean, that's the big question, right? It feels like it should be impossible. You're basically looking at a skyscraper-sized vehicle getting lifted into the sky by a controlled explosion. It's wild. But, it's not magic. It's this beautiful, intricate dance between some serious engineering and the basic laws of physics. And we are going to break down exactly how that dance works. Okay, so it all kicks off with one simple, totally non-negotiable rule. Before a rocket can even think about lifting off, it has to win this fundamental battle of forces. And here's that battle laid out super simply. On one side of the fight, you've got your upward force. That's the thrust coming from those powerful engines. And on the other side, pulling it down, you've got two opponents: the rocket's own weight, thanks to gravity, and drag, which is just a fancy word for air resistance. So, for that rocket to even budge an inch, its thrust has to be stronger than its weight and the drag combined. It's got to win that tug of war. And where does that incredible thrust come from? Well, it's a perfect textbook example of Newton's third law of motion. You know the one. For every action, there's an equal and opposite reaction. The rocket throws a massive amount of superheated gas down, and in reaction, that gas pushes the rocket up. It's such a simple idea, really, but it's powerful enough to literally launch us to the stars. But it's not all just about brute force. Launching a rocket is also about insane precision. I mean, way before those engines even think about igniting, there's this critical, meticulous sequence that has to play out absolutely perfectly. And that's the countdown. And that countdown you hear, that's not just for dramatic effect in the movies. Every single step is a super high-stakes checkpoint. First, you've got computers running millions, and I mean millions, of checks on every single system. Then they start loading up thousands and thousands of gallons of extremely volatile propellant. After that, the navigation systems need to be aligned to a pinpoint degree. And finally, you get to that nail-biting moment where every single team leader has to give their final go for launch. And there are absolutely no do-overs here. A single bad sensor reading, a tiny shift in the weather, even a communication glitch, any of it can trigger a no-go. And that means the whole mission gets scrubbed, aborted, to make sure the vehicle and, more importantly, any crew on board is safe. Everything, and I mean everything, has to be perfect. All right, so the countdown was perfect, the rocket is off the pad, and it's just screaming its way into the sky. But get this, one of the absolute most dangerous moments of the whole flight happens just about a minute after liftoff. It's this perilous point in time called max Q. So, what is max Q? Well, it stands for maximum dynamic pressure. The easiest way to think about it is this. It's the exact moment the rocket is getting hit with the strongest punch the atmosphere can possibly throw at it. We're talking about immense, incredible physical stress on the rocket's frame, and it's all caused by these two factors that are kind of fighting against each other. So on the one hand, factor number one, the rocket is accelerating like you wouldn't believe. It's just picking up speed, going faster and faster and faster. And that means it's slamming into the air with more and more force. But at the same time, and this is factor number two, it's also climbing higher and higher. And as you go up, the atmosphere gets thinner, so the air it's hitting is becoming less dense. Max Q is that perfect, dangerous storm. It's the moment when the rocket's speed is incredibly high, but the air is still thick enough to create the absolute maximum possible strain on the vehicle. So how do you get through that? How do you survive it? The solution is actually really clever. Just as the rocket is about to hit max Q, the engineers do something that sounds counterintuitive. They throttle the engines down. Yeah, they actually ease off the gas for a few seconds. This reduces the pressure and lets the rocket cruise safely through that zone of intense stress before they throttle back up to full power on the other side. Pretty smart, huh? Okay, so pushing through the atmosphere is one challenge, but here's another one. How do you stop this giant metal tube from just, tumbling end over end? It all comes down to one word: stability. And this right here, this is the secret sauce. A rocket has two really important invisible points on it. There's the center of gravity, that's basically its balance point, and then there's the center of pressure. which is where all those aerodynamic forces are pushing on it. Now, for the rocket to fly straight and stable, the center of gravity has to be ahead of the center of pressure. The best way to picture this? Think about a dart. The heavy tip is at the front, right? That's its center of gravity. That's why it flies straight. If you tried to throw a dart backwards, it would just flip around and tumble. Rockets use that exact same principle. It's just, a much, much bigger dart. Okay, so our rocket is stable. It survived Max Q. Now what? How does it actually get up to the mind-boggling speeds you need to reach orbit? Well, the answer is hidden inside this really elegant piece of math, an equation that pretty much unlocked all of space travel. Here it is, the Tsiolkovsky rocket equation. This thing is like the secret code for getting to space efficiently. It tells you exactly how much you can change a rocket's velocity. And the key, you might be surprised to hear, isn't just about having bigger engines. It's all about the mass. So let's break down what that fancy equation is really telling us. As a rocket burns its fuel, what happens? It gets lighter. And we all know from basic physics, it is way, way easier to speed up something light than something heavy. So here's the brilliant, kind of counterintuitive part. The less the rocket weighs, the more speed it gets from the exact same amount of engine push. This one simple idea is the entire reason we have multi-stage rockets. They are literally designed to do something that sounds crazy. They throw away huge parts of themselves. Those giant empty fuel tanks are just jettisoned into space so that the remaining rocket is much lighter and can go way faster and farther. It's not just about carrying fuel, it's about knowing when to get rid of the dead weight. So there you have it, from a simple battle of forces to a nail-biting, perfect countdown, and finally, to an elegant equation that's all about losing weight to gain speed. These are the core principles that took us from a launch pad right here on Earth all the way to the moon. And it kind of leaves you with this one big fascinating question, doesn't it? If this is the physics we had to master just to escape our own planet's gravity, what new physics, what incredible breakthroughs will we need to master to take that next giant leap to the stars?